welcome. In this session, we'll explore a simple iteration that attempts to numerically estimate where a minimizer is for a function that has a scalar argument. So a first-order approximation using a Taylor series is that we can say the function exactly equals the function evaluated at some expansion point or estimate plus the first derivative of that point times the free variable minus that estimate plus this is the Lagrange remainder. So what this says is that all the remainders can be captured as a second derivative term. And what we can do is let's change the variables. So we'll represent this free variable t as being our expansion point minus a secondary variable, which we'll call s. So when we do this, let's observe that t minus t1, which appears repeatedly, is t1 minus t1. So that's just minus s. So everywhere we see this t minus t1, we can just substitute a minus s. And what this would mean is we can approximate the function at some offset from the expansion point as being approximately the function at the expansion point minus the first derivative of the function at the expansion point times this free variable s. So this lets us represent a function as a local linear approximation using the Taylor series that we recall from long ago prerequisites. So another way to think of this is a step of size s along this line. So this is defining a line. So now let's combine all of this. Suppose that we are at some place in our iteration and we have a value t sub k. And let's suppose that the derivative at this is less than 0. Then what that means is the function is sloping down and the minimizer has to be to the left of tk. Then suppose at some point that the first derivative is positive. So that means the function is sloping up, and that means the minimizer is right of it. So that means that the direction of the minimizer from our current point is a direction, and it's minus the first derivative evaluated at the place that we're at right now. The approximating line is then exactly what we said, which is, so we can represent the approximating line as the function evaluated at our current point plus a multiple of the direction. And what we ask is the user provides this hyperparameter s, which we call step size, and in neural networks this is often represented as the Greek value eta. So the fixed step size iteration gives us a sequence of points. What we say is from the current point, let's add the user provided multiple of the direction, and that gives us the new point. Now, a problem is if this user provided hyperparameter is too large, then the iteration won't converge. It might go off to plus or minus infinity. It might oscillate. It might have high error. There are lots of behaviors associated with it. If the user provides a step size that's too small, we can get convergence that's too slow. We can also get high error, and we can get other peculiar behaviors. So it's the user's responsibility to select this hyperparameter. Some advanced methods that we can learn in a subsequent course are how to algorithmically tune the user-provided step size. So let's go through a simple algorithm. What we'll do is we'll say that the number of iterations is provided by the user. There's the user says stop when things get really flat. So when the first derivative gets close to 0, you can stop. And what we'll do is we'll set up our free variable as being the user provided initial estimate. And we'll say that our current estimate of the function is we evaluate the function at this value. And then we set the direction to be the negative first derivative of the function. We'll start at k equals 0, and we'll say while we're not converged. So this is something that we go through in the notes. For now, we'll just say when it has hasn't converged, what we do is we set our new estimate as our old estimate plus the step size times the descent direction. We set the direction now to be the negative first derivative of the new point, and we set the current value to be the function, and then we say increment our counter, and we are done. So the fixed step size computation looks simple, and it is simple, but it's a very, very powerful iteration. So now let's go through an example. Let's suppose that we have this function and we have this starting point right here, and we're going to use a step size of 0.4. So what will happen is if I take one step, I get here, and you can see that it's gone on the other side of the minimizer, and it's actually increased the function value, right? If I take another one, it'll go here, and what will happen is we're going to get very erratic progress. We're going to be jumping back and forth around this minimizer, and it's not going to converge. Now, suppose that I pick a step size that is 1/10, right? That's much, much smaller. What will happen is we'll start here, and then we'll creep very, very slowly towards the minimizer. So we'll get there, but it's going to have very slow convergence. So when we're doing any kind of numerical optimization, picking the step size, which is a hyperparameter provided by the user, turns out to be non-trivial, and it can be very, very difficult. And in neural network research, people always specify the learning rate or the step size that they're using. So what have we learned in this class? Well, you should now be able to develop code for the basic iteration. We use MATLAB. You could use Python. That you should be able to test the effects of different values for the step size, and you should be prepared to explain the iteration behavior if we give you some simple functions.